This is Mrs. O'Neill for Chapter 5, Section 2, Part 3, your practice problems. So in the orbital filling diagrams, as a review, as a reminder, you always want to go from the lowest energy to the highest energy. You also want to remember that all the boxes available for that sublevel has to be filled up first. So first of all, you have to draw all of those boxes, whether they're filled or not, but they have to be filled before moving on to the next sublevel. You also want to remember one electron in each of those orbitals in each of those boxes before pairing up. So for instance, in the P sublevel, you always have 3 orbitals, which means you have 3 boxes. Even if you only have 1 electron in that P sublevel, you will have to draw all 3 boxes. If you have 4 electrons, that means you draw 3 boxes, 1 in each orbital before you pair up the first guy. Okay, and as a guide, use your notes, right? Use the orbital filling diagram, and you want to pay attention to this over here. On the right side is the actual ordering of filling, because here, this might be a little confusing, especially gets a little squished here. So this is your order of filling in order of energy. So it's easier just to kind of go by this. And that's going to be very, very the same as your electron configuration diagonal rule. So either one that you want to use as a guide will help you understand the energy order. Okay, so draw the orbital diagrams for these 5 elements. It is up to you if you want to do one at a time and play the video to check your work, or you want to do all of them at one shot and then play the video to check your work. So for lithium, the first thing to look at is how many electrons you have, and then start filling up according to energy. So at this point, you should have paused, or you're going to pause now, and you're going to draw however many boxes you need per sublevel in order of energy, lowest to highest, and then put in those arrows, one up, one down, for that spin. So you should have drawn 1s for 1 box, 2 electrons. So 3 minus 2 gives you 1 more electron. So I'm going to draw the 2s orbital, or the 2s box, with 1 electron. Again, notice the arrow up and arrow down. You could also draw it with lines and then just half arrows. It doesn't matter to me, but you do need to draw either the line or the box. And I always say boxes, that to me is just easier to visualize. And you also have to label the boxes. You should not just have 2 boxes here. You need the one box to be labeled as the 1s and the other box to be labeled as the 2s. Otherwise, I do not know what orbital sublevel you're talking about. Okay, 14 electrons for silicon. You should have drawn the, again, 1 box for 1s, 1 box for 2s, 3 boxes for 2p's, and at the moment they're all filled up. 1 box for 3s, and now for your 3p, notice I drew all 3 boxes even though there's only 2 electrons, and 1 in each box before we would even think about pairing up. So that's what the orbital filling diagram for silicon should look like. This is the one for iron. Again, notice now I didn't use boxes, I just used lines, but I still use the arrows up, arrow down, and I still labeled each of the sections. So I have the 2p section labeled, the 3p section labeled, and your 3d. And notice I still draw all 5 lines or all 5 boxes for that 3d, whether they're all filled or not. How about for carbon? Did you get that? And again, here's the electron configuration, very similar to the orbital filling diagram. So again, the boxes are the orbital filling diagrams. That's a little bit more detailed as to where those electrons are per orbital. And the electron configuration is just that, using that diagonal rule. How about for argon with 18 electrons? It's a noble gas. It's in group 18, so all of its orbitals should be filled up. And now the electron configuration reminders. So again, you're using your diagonal rule or the periodic table as your guide. You're going to follow those arrows. And remember, you want to count those electrons. And the S's have 2 electrons maximum, P's have 6, D's have 10, and F's have 14. That you should know by now. So again, you're either following the arrows or using the periodic table as a guide, which is your best bet because that's what you're going to be able to use on your test. It's going to be a periodic table provided for you, not the one you've been using in class. Or again, you can just think about that orbital filling diagram, the rules and the energies. So I want the full electron configuration for these particular elements. Again, the first thing I would do is find them on the periodic table. I would find how many electrons they have, and then I would just start filling up, start using that periodic table as a pattern, as a guide. So for beryllium, that's what you should have. And I can also ask you about this. For beryllium, since it's the S section, I can ask you how many valence electrons there are. And for beryllium, there's 2. For phosphorus, it's 15 electrons, and the ending is the S and the P's. So again, I can ask you for valence electrons for phosphorus. So the last or highest energy level, I should say the highest, that's a better terminology, the highest energy level, and in this case is the 3rd energy level, but it has S's and P's. So 2 plus 3 gives you 5 valence electrons. Bromine has 35 electrons total. And if I look at the highest energy level, again, not just the last, but the highest, I can now ask you again for valence electrons. So 2 and 5 give me 7 valence electrons, and that should make sense because it's in group 17. Here's nickel, and it has 28 electrons. I'm not going to ask you about valence electrons for nickel because it's in that groups 3 through 12. Those are the transition elements, and they get a little confusing. Here's zirconium, and yet again, I cannot ask you for valence electrons because it's in that weird section. I can only ask you for valence electrons according to the S and the P groups, but make sure that you're doing this in the correct order. I will be looking for the correct energy order when you're doing the orbital filling diagram or the electron configuration. Now, there are 2 exceptions to the electron configuration that you must know. There's a bunch of exceptions, but 2 that you must know. Elements chromium and copper. So let's take a look at these guys. So chromium has 24 electrons, and this is the electron configuration that's expected. So again, on your notes, make sure that you write what you would normally do. However, this is actually wrong. The 4s2 and the 3d4, they do something else. They kind of change things up a bit. They actually have one electron from the S actually moves to the 3d section. Now you're wondering why. Well, because it actually gives us 2 half-filled orbitals. So the S and the D both would be half-filled, and this actually makes a more stable atom. So here, let's look at what happens. So here's our 4s, has a slightly less energy than our 3d. So this is filled, and now our our D section, right, our 3d section has 4. But what's going to happen here is that one electron is going to kind of move over, and now what happens is that energy, look at that energy now of the S and the D section is going to be equal. So because that energy now kind of stabilizes itself, it's actually more stable as an atom altogether. So it's better to have 2 half-filled sublevels that are real close in energy than it is to have the S filled and the D in only having 4 electrons. So this has a slightly lower energy altogether, and that's going to be more stable for that element. Copper kind of follows the same rule in a slightly different way. So again, this is what's expected of copper, the 4s2 and the 3d9. But what happens here is the 4s1, one of those electrons, moves over to the D. So what does that give us? That gives us that half S sublevel, but it fills up the 3D sublevel. And what happens is that now becomes more stable. Having that full D shell kind of brings down that energy a little bit, and the 4s1 and 3d10 now together make a more stable element. So here's our general rule. These are the exceptions to the rule. So anything that ends in a S2D4 is really going to be an S1D5. And the same thing with our S2D9 is going to give us S1D10. It's going to be more stable. So look at the periodic table. Think for a moment and see if you can come up with any other elements that would follow this pattern. Hopefully you came up with elements that would be in the same group as chromium and copper. So the two elements in chromium would be Mo and W for tungsten, and in the copper group would be silver and gold. So they probably follow this same kind of pattern or the same exceptions, but you are only responsible for chromium and copper. So now let's look at that shorthand electron configuration. So as a reminder, hydrogen is one electron, so he's just going to be the 1s1. Okay, so again, as a reminder, that big number is the period number. That little letter is going to be your S block, right? Whatever block it's in, and your little one is talking about the how many electrons are in there. So remember that F area, though, is slightly different, right? The PT and every periodic table is slightly different. So we have to be careful with our F level. So remember that the F level really it starts at atomic number 57. Sometimes that number 57 is in the main part of the periodic table, and sometimes they pull it out and put it on the down. So it really just depends. So we have to really be careful because sometimes those elements are placed in the D. So we're just really going to go by, again, by electrons, electron order or atomic number order. So what do I mean? Remember that the periodic table really looks like this. So again, in row 6 or in period 6, this is your 6s, but then it starts your 4f, right? -2 in the F section. So remember, this is sometimes pulled out. And when it's pulled out, sometimes the F sections are in the main part of the periodic table, and sometimes they give you the D. So it really just depends. So again, always look at the atomic number. You're going to go in atomic number order and then count to 14. And then if your D starts here or the D starts here. It is kind of confusing, but that's why we go by electron order, right? Atomic number order. So can you do the shorthand for these particular elements? So again, for germanium is a number 32. So the first thing I'm going to do is I'm going to look at the noble gas before him. Whatever that noble gas before him, in this case it's argon, that's going to take care of most of my electrons. Then I'm going to finish the shorthand electron configuration like I would do the normal configuration. The only difference is I don't have to fill up 1s2 and 2s2. I don't have to do all of the electron configuration because part of it is filled up already from the argon. So we're going from argon, and now what's the next section down here is going to be the 4s2. This whole section is filled, so I'm going to give that the 3d10, and now this is our P section, and there's 2 of them, 2 electrons there, so the 4p2. So again, it's the noble gas before, and then filling up the normal electron configuration as you normally would. Helium has 2 electrons, so helium is its own shorthand because it's a noble gas. There it is for silver. Now, for our purposes, this top one would be fine, but if you caught on, again, silver is one of those that probably follow that exception to the rule. But I'm not worried about silver. I'm more worried about chromium and copper. Here's uranium shorthand. And again, this one might be a little tricky because it is in the F section. And here's potassium. And so now, how about if I go the other way, give you the electron configuration, and I want to know the elements? Well, the biggest thing is count those electrons, count those little exponents. The number of electrons is going to give us the atomic number, and that atomic number would give us the element. So pause the video, count up these electrons, and find that element. So you should have gotten this as an answer. So again, if you're having issues with this when we do our bookwork, please call me over and get me to do some extra problems with you. All right, we'll see you in class for bookwork and practice problems.